Okay, in this video we're going to talk about matrix algebra, which is about operations you can do with matrices. And we've seen how to add vectors and how to multiply a matrix by a vector. And we're going to extend that to working with matrices. And in this video I'll just present the main results without giving proofs. But there are some interesting theorems in this section. So first of all, there's addition of matrices. So let's say that you have two m by n matrices. A and B. So two m by n matrices A and B can be added just by adding the entries. The corresponding entries. So for instance, if you have something like A equals, the first column is 5, 11, 4, the second column is 3, 6, 6, and B is the matrix whose first column is 8, 3, 8, the second column is 5, 6, 10, then you can just add them. A plus B will be the matrix that you get by taking the ij entry. So you take A sub ij and then add B sub ij. So to get the sum, it will also be an m by n matrix. In this case, it's a 3 by 2 matrix. You just add the corresponding components. So I add the 5 and the 8 to give 13. And then if I add by column, then I'll do 11 plus 3, and then 4 plus 8. So I'll get 14 and 12. And then the second column will be 8, 12, 16. Right? So pretty straightforward, not a whole lot to say about that. And you can also take a scalar multiple to scalar multiplication of a matrix. So that's also easy. If you have a matrix A and a scalar C, then you can define this new matrix C times A, which is going to be the matrix where the ij entry is formed by taking the ij entry of A and then multiplying by C. So for instance, if you have that first matrix A, okay, let's say you multiply it by 12. So 12A, so here's an example. 12A is just going to be what you get by multiplying each entry by 12. So you're going to get 60, 132, 48, 36, 72, 72. Okay. By the way, let's just clarify that we say that two matrices are equal if, so let's say that the matrices are A, where the ij entry is written A sub ij, and B, where the ij entry of B is written B sub ij. So equal if for all I and j, A sub ij equals B sub ij. In other words, all the entries match. Okay. And this scalar multiplication and addition of matrices have these properties. Oh, I should maybe also mention that there's something called the zero matrix. The m by n zero matrix is just the matrix where, as you might expect, all the entries are 0. Okay? So you have a zero matrix for each m and n. Okay. But I'll usually just write it as 0. And you cannot, we don't define addition of matrices that are not of the same m and n, the same size, right? So you don't define a 2 by 2 matrix plus a 2 by 3 matrix, okay? Also, using scalar multiplication of a matrix, you can define subtraction of a matrix. So this is, let me just indicate the different things going on. Scalar multiplication, two matrices are equal, the 0 matrix. And then, of course, you just define A minus B to be the matrix that you get when you do A sub ij minus B sub ij. Okay. So now we have these properties of matrix addition, which is that A plus B is equal to B plus A. Again, when I'm writing this down, I'm not writing all this out, but when I'm writing this, the assumption is that A and B are the same size, right? So I didn't write down if A and B are the same size, then A plus B equals B plus A, but that's assumed when I'm writing this. I'm assuming that A and B can be added in the first place, right? Okay, well, why is that true? Because what I'm doing to add the matrices is I'm just adding the individual entries. And when you add two numbers, it doesn't matter which order you add them in, right? If I have two numbers, x and y, then x plus y is the same as y plus x. Okay. So that's basically why this is true. And the other one is, let's say I have a scalar c, and I do c times the matrix A plus B, that's the same as C times A plus C times B. Okay. And again, this is C is a scalar. I'm assuming that you can add A and B. Otherwise, this equation doesn't even make any sense. Number C, property C is that if you take two constants, maybe R and S, and then add them, and then scale the matrix A by that, that's the same as taking RA and then adding SA. Again, all of these A, B, and C properties follow just from properties of real number addition. Okay. And part D is the associativity, that if you take A plus B and add the matrix C, that's the same as taking A and then adding the matrix, which is B plus C. So this first one is the commutativity of matrix addition. And this part D is called the associativity of matrix addition. And another property is if you have two constants, R and S, you multiply them and then multiply by A, that's the same as taking R and then scaling the matrix SA. And then part F is if you take any matrix and add the 0 matrix, then you just get A. Well, that's really obvious, right? Because you're just adding 0 to all the entries in A. Of course, you're not going to change the matrix. So I just wanted to write them down, but they're all essentially obvious. They're just apparent from the way that you add matrices. So now it's time to move on to matrix multiplication. Matrix multiplication is more complicated. So matrix multiplication the way we'll define matrix multiplication can be thought of, it can be motivated by thinking about the composition of two functions. So recall that when you have two functions, let's say you have a function from a set x to a set y, and another function g from the set y to the set z. So if you have these two functions, then you can define the composition g of f to be the function. So to say what the function is, I have to tell you what it does to an input. What it does to an input x is it maps it to g of f of x. In other words, if you have, here's a set x, here's a set y, f is taking x to y, g is taking y to z. And notice that, when I say that g is taking y to z, I'm not saying that these maps are onto, okay? It's just that the target of f is y and the target of g is z. When you have this, so you have x here, that will go to f of x here, and then g will take that to g of f of x. And then the composition is what you get by, it's the function that you get by doing f and then g. So that's g composed with f. So for instance, if you have f of x equals, say, x squared, and g of x equals cosine x, then g of f of x would be cosine of x squared, and then f of g of x would be cosine of x in parentheses squared. Now, in general, these are not the same thing, right? G composed with f and f composed with g are just completely different functions. These are different functions. Well, remember, when you have two matrices, you're going to get a linear transformation. That's a type of function. So the question is, what happens when you compose two linear maps, or two linear transformations, same thing. Let's look at an example. So let's say that you have this matrix A, which is the matrix whose first column is 2, 1, the second column is negative 1, 3, and then you have this matrix B where the first column is 4, negative 1, second column is negative 2, 1. Okay. What happens if you, so here's a little picture. So here's R2, right? Let's say that you do B first. So you take the function t sub b, that takes the vector x and maps it to b times x, right? B times x is a vector in R2, and let's say that you compose that with t sub a. Well, t sub a also takes vectors in R2 to R2, and t sub a is going to take bx to a times bx. Okay. So what is the matrix, or how do you describe the function if you think of this composition as a single function? What is that function? So that's the question that we're going to answer. And the way to do it, remember that the linear transformation is defined by where it sends the standard basis vectors. Once you know where the standard basis vectors go, that determines the entire transformation, because remember the reason why that's true? Because every input x is a linear combination of the standard basis vectors. It's just x1 e1 plus ... xn en. And then when you apply a linear transformation, by the linearity, it will go to the corresponding linear combination of the outputs of the standard basis vectors. So we really just need to know where E1 and E2 go. So let's see where E1 goes. Well, E1 is 1, 0, right? Now where is that going to go? When you apply B to it, it will go to B times E1. Remember, where do you see B times E1 in the matrix B? It's the first column, right? If you take B and multiply it by 1, 0, you get the first column. So you know that you're going to get 4, negative 1. And so therefore, when you apply A, when you do A times it, you're going to get A times 4, negative 1, which ends up being, so you're taking a matrix times a vector, you're going to get 9, right? Because 8 plus 1 is 9, and then 4 minus 3 is 1, so you get 9, 1. Okay, what about, so E1, 1, 0 is going to go to 9, 1. Now what about E2? Where's E2 going to go under this composition? Well, E2 is 0, 1. And first, T sub B is going to map it to B times E2. And that's going to be, where is that in the matrix? How do I know what B times E2 is? It's the second column of B. So I'm going to get negative 2, 1. And where's that going to go? Well, of course, that's going to go to A times negative 2, 1, which ends up being negative 4 minus 1 is negative 5. So you get negative 5, and then negative 2 plus 3 is 1. So you get negative 5, 1. Okay? So the composition is going to send 1, 0 to 9, 1, and it's going to send 0, 1 to negative 5, 1. Well, let's see. It's going to send x. Okay, let's see what happens. So it's going to map 1, 0 to 9, 1 and 0, 1 to negative 5, 1. Where is it going to send a linear combination? Let's say that I had a linear combination. So I have this random vector x, which is x1, x2. Well, this is equal to x1, e1 plus x2, e2, right? So this is going to go to b times x, and this is equal to b times x1, e1 plus x2, e2. And now by the linearity, this is x1, b, e1 plus x2 times b times e2. Okay, now that is going to go to a times bx. So let's write down what a times bx is. A times bx is equal to a times, we figured out what b times x is. It's x1 b e1 plus x2 b e2. And so by the linearity again, this is going to be x1 times a times be1 plus x2 times a times be2. And this is going to be x1. We figured out a times be1, it's 9, 1, right? So x1, 9, 1 plus x2 times negative 5, 1. Now, what is this? We can write this as a matrix times a vector. We can write this as the matrix 9, 1, negative 5, 1, those columns times the vector x1, x2. So what we've discovered is that the composition which is T sub, let's see, we did T sub B first, right? T sub B, so it's T sub A composed with T sub B, because you do T sub B first. This has standard matrix (9, 1, negative 5, 1). And where did the 9, 1 come from? It came from, we got the 9, 1 from here, right? It was A times 4, negative 1. And A times 4, negative 1, well, we did that because we did A times the first column of B. So let's write that down. So this first column is A times column 1 of B. And the second column is A times column 2 of B. Now this matrix is what we call this matrix the product of A and B. And naturally we write this as AB. Okay? So in general, well, let's just write this in. So AB is this matrix that you get by taking the first column to be A times the first column of B, and the second column is A times the second column of B. And what this is the standard matrix. It is the standard matrix of T sub A composed with T sub B. Okay. So there's a few ways to say this. So if you do AB, if you multiply it by the vector x, this is going to be what you get when you take A and multiply it by bx. So this is by the way we defined A times B. Another way, if you want to phrase this, so this is for all x and r. Well, in the domain, right? So here I had a specific example just to illustrate the general definition. But it would be an R. If A is an m by n matrix, then it'll be for all x and Rn. Sorry, you have to multiply by B first. So it's okay, let's not, because I didn't say what size A and B are. Let's just say for all x. Okay. And another way to phrase this is that the linear transformation given by AB, this is equal to the linear transformation given by A composed with the linear transformation given by B. So that's the case of the 2 by 2 situation. And now let's just define the matrix multiplication, the matrix product in general. So in general, if you have a matrix A, which is an m by n matrix, and B is an now let me, I want to be consistent. I did B first. Okay, let me okay, it's n by k. Okay, then A times B is the m by k matrix So this is the definition of the product. We're defining the product AB to be the m by k matrix whose jth column is A times the jth column of B. In other words, I take the matrix whose first column is A times the first column of B. Okay, that's the first column of A times B. Then the second column of A times B is A times the second column of B. And then you keep going, and you have k columns because B is n by k. So then you have A times the column k of B. That's the last column. And that gives you the matrix. And so this is an m by k matrix. Now, in order for this product to be defined, the n here have to be the same. So what in terms of the picture, what's going on is you have this matrix A that's taking vectors in Rn to vectors in Rm, and you have this matrix B that's taking vectors from Rk to Rn. So in order for the composition to be defined, right, you need the target of TB has to be the same as the domain of TA. So you have to have that in order for you to have the composition. So that's why we define the product to be the way it is. So let's do an example. So let A be 3, -2, 1, 0, B to be -1, 4, 0, -3, -2, 1. Find A, B. Well, it's going to be, so let's call the first column of B, B1, second column of B, B2, and the third column of B, B3. So this is A is a 2 by 2 matrix, B is a 2 by 3 matrix, and notice that the numbers 2 and 2 match up. So we do get a matrix A times B, and the first column is A times the first column of B. So it's just A times B1. So A times B1 is this matrix times -1, 4. And this is going to be 1, 2. If I do A times B2, I'm going to get 0, no. I'm going to get -3, 0. And if I do A times B3, I'm going to get -5, +4. And so my product, A times B, is going to be the matrix 1, 2, -3, 0, -5, 4. Right? Because this vector is my first column, that vector is my second column, that vector is my third column. Okay, what about B times A? Well, B times A is, there's a bit of an issue because B is 2 by 3, A is 2 by 2, and the numbers don't match up. So BA is undefined. So when you have matrix multiplication, it doesn't work the same as multiplying numbers, right? If you multiply two numbers, okay, x and y, then x times y is the same as y times x. Well, if you have two matrices, you can have A times B as a matrix, but B times A is not even anything. It's undefined. Right? There's no such thing as B times A. And I just want to, emphasize the reason why. I mean, it looks like a weird definition. Why do we multiply matrices this way? The reason is that when you multiply matrices this way, you get the standard matrix of the composition. So that way, when you do AB times X, you get the same as what you do when you do A times the vector BX. Okay. This is a kind of, let's see, should I stop the video? Maybe I'll add one more thing. So let's say that you have a square matrix. If you have a square matrix, A, square matrix. So let's say an n by n matrix. What happens if you take the identity matrix A times I, n? So remember I sub n is the matrix, the n by n matrix, where the diagonal entries are all 1. What happens if you do that? What's A times the n by n identity matrix? You're going to get A. Okay, you can check that if you take A times the first column of the identity matrix, you're just going to get the first column of A. And if you take A times the second column of the identity matrix, you just get the second column of A. Therefore, when you do A times the ni, and you keep going, A times the jth column of the identity matrix is just the jth column of A. And so what you get when you put the n columns together, you just get the matrix A, right? Because A times column J of the identity matrix is equal to the jth column of A. And similarly, the n by n identity matrix times A is equal to A. Why is that true? So if you have this identity matrix and then you multiply by the matrix A, let's write the columns as column 1 of A to column n of A, then when you do when you multiply, there we go. Let's call this vector maybe x1 and then the nth vector xn. We know that when you take the identity matrix and multiply by a vector x, you just get x, right? So if you multiply by the ith column vector, you just get the ith column vector. And so therefore you're not changing any of the columns, and so you're going to get A. Okay. This is the key fact that you're using, that when you take a matrix times a vector, if your matrix is the identity vector, the identity matrix, you're not multiplying, you're not changing the vector. Okay. Okay, I think we should make a separate video for the other stuff about matrix multiplication, because there's kind of a lot to say about matrix multiplication. But the key thing to know is the way we defined matrix multiplication. We defined the product of A times B, if A is n by n and B is n by k, we defined the product to be the matrix whose jth column is A times the jth column of B. So this is sort of the more modern way of thinking about matrix multiplication. There's another way of thinking about matrix multiplication that we'll get to, but this this concept of working with the columns of B, okay, and thinking about matrix times a vector, and then just putting those resulting vectors together as the columns of this new matrix, that's a more, that's something that's been emphasized more recently. And it is important to understand matrix multiplication this way, to understand just matrices in general and how they work. And again, the reason why we defined it like this is so that this way A times B describes what the composition of B, of multiplying a vector by B and then multiplying the resulting vector by A, the composition of T sub B and T sub A, or T sub A and T sub B. Okay, the one where you do T sub B first and T sub A second, that composition, A times B, is the standard matrix of that composition. Okay, more on matrix multiplication in the next video. Thanks for watching.